So one other type of delta H value that we will see is something called the standard enthalpy of formation. And where these come from, it's because delta H is a state function. Which, if you remember, it means it doesn't matter which way we go, just where we started and where we ended. A state function. We can set any point as our 0 point. So we have rules because someone else made up these rules that have been standardized and they work really well. But, these were chosen as a 0 point. Now, what's really useful about them is by choosing these as a 0 point, it sets a reference that gives us another way to get delta H reaction. So it will look a little different, and I'll tell you what you need to look for to know when to use these. But it is another way that we will be able to get delta H reaction. Now we need to do some definitions, right? Because someone set 0 points in definitions, so we should go through those. But then we'll get into how you can use these. So they're standard enthalpies of formation. So we need a definition for something called the standard state. And something is in its standard state when it is a pure gas at 1 atmosphere of pressure and 25 degrees Celsius. If it is a liquid or a solid, it's pure, it's in its most stable form. It is at 1 atmosphere of pressure and 25 degrees C. And if you have a solution, it is also at 1 atmosphere, 25 degrees C, but its concentration is exactly 1 molar. So if anything meets these conditions, it's in its standard state, which means that we can calculate a standard enthalpy change. So it's still delta H, but now it has this little circle in the upper right corner. So delta H with a little circle means standard enthalpy change. And now this is just the change in enthalpy for a reaction. When all products and reactants are in their standard states. All right, well, it hasn't technically helped us yet, but we know what a standard state is, so we can identify if the products and reactants are in a standard state. So I guess we can use that to figure out a standard enthalpy change. And we will do it using something called the standard enthalpy of formation. So it's a delta H with a circle because it's a standard and a subscript F because it is for formation. So for a pure compound, the standard enthalpy of formation is the change when 1 mole forms from its constituent elements in their standard states. We're going to look at what that means and how we use it. And to go with this, so this was a compound for a pure element in its standard state. Its standard enthalpy of formation is 0. So 0 for elements in their standard states. For compounds in their standard states, well, it's the change when all of the elements react. So let's look at first what it would look like and then where we can find them. So for something like C6H12O6 solid, so the solid is the most stable form at 1 atmosphere and 25 degrees Celsius. So the delta H standard formation value for this compound comes from a reaction that would look like carbon, because it's one of the elements. I need 6 of them. Its standard state and most stable form is graphite, plus the standard state for hydrogen is H2 gas, and so I need 12 total, so I need 6 of those. And then O2 is the standard state for oxygen gas, so I'm going to need 3 of those. All of those things turning into C6H12O6 solid. Now, we aren't necessarily going to use this specific reaction, but if we go to your very favorite Appendix 2, you will find delta H formation values. So I'm going to go grab a screenshot and then bring it back. Okay, so I don't actually know if the screenshot will already be here, but this is one of the columns from those giant tables that we've not yet looked at in Appendix 2. It's Appendix 2 in the TRO textbook. If by the time you watch this we're on a different textbook, it might be a different number, but the table's going to look the same. So the C6H12O6 solid that we just talked about is in this table. I think C6H12O6 solid glucose. Let's get that highlighted. So there are 3 columns of data. The first one is where we are right now. So these delta H of formations. We will talk about the other 2 columns when we get into a later section on thermodynamics. But this piece right here is the delta H formation for glucose. So that means that this reaction, as I've written it, has a delta H reaction equal to negative 1273.3 kilojoules per mole, because this reaction is written for the formation of glucose. So that's what these numbers mean. And the really great news is that in this table, something like this, if you forget about the whole rule for elements, if you go look up something like H2 gas, you're going to see that it just lists 0 for the delta H of formation. So the table will kind of tell you when you forget. However, we do not typically need to use these formation reactions because everything that we do is probably not going to have just pure elements in their standard states. It's going to have a bunch of other chemicals. And if we were to go through the process of Hess's law, we could write these formation reactions for everything and add them up. Or we have a formula. So if you need to calculate a standard enthalpy of reaction using enthalpy of formation values, you will do the sum of the number of moles of products times the delta H formation of those products, and then subtract the sum number of moles of reactants times the standard enthalpies of formation of the reactants. So we will do an example with this, but this is, look, it's products minus reactants, which is final minus initial, and then we use these N values because each is in kilojoules per mole and it's extrinsic. It depends on the exact amount. So it's going to depend on the stoichiometry of your reaction. An example of what this might look like is that you could just be given the problem, find delta H reaction standard for, and then you're given a reaction. So I'm going to put the reaction in a second. The key here is this little circle at the top. If you see the little circle, it means you can use enthalpies of formation. So the reaction we're doing is 4NH3 gas plus 5O2, also a gas, turning into 4NO gas plus 6H2O gas. The states matter very much so because it could mean the difference between something being in its standard state or not. And this is the whole problem. We don't get any other information. I guess unless you have a molecule that doesn't appear in the appendix, you might have some of that information in the problem, but this could be it. So we're using the clue that we have that little circle that means standard. To know that, we can use standard enthalpy of formation values, and they all come as kilojoules per mole. So I'm going to make a little table here. Now, what you should do as you're practicing this is make the list, right? NH3 gas, O2 gas, NO, and H2O. Pause here, go to the appendix and see if you can find these values on your own. Now when you do, all right, you have a second to pause. All right, now when you do, you should find that NH3 says negative 45.9, O2 says 0, NO says positive 91.3, and H2O says negative 241.8. So our delta H reaction, it's going to be the sum N products, delta H standard formation for the products, minus the sum number of moles of reactants, standard enthalpy of formation for reactants. So I'm going to jump down just so that, because this is going to be kind of long, delta H reaction equals, I recommend always just putting brackets so that you don't lose a negative sign somewhere. The products are 4 NOs, that's 4 moles, times the value for NO was 91.3 kilojoules per mole, plus, because it's a sum, so I'm going to add all the products together. The other product was water, and there are 6 moles of water, times negative 241.8 kilojoules per mole. That's the end of the products minus the reactants. There are 4 moles of NH3 at negative 45.9. Plus, well, it doesn't actually matter how many moles of oxygen. It's 5, but 5 times 0 is still going to be 0. So that won't be involved at all. So then, I don't have the individual values, but right, just if you need it for a little bit of sanity, you can calculate these values individually before you add them together to make sure you don't miss anything. And this ends up being negative 902.0 kilojoules for the reaction as it's written. So I could put this back next to the reaction, still kind of put that per mole back in there if I need it for a conversion, although technically I canceled it out. So So this is an exothermic reaction.